Any content questions about the class? Okay, so today's topic is 1 degree of freedom oscillator, forcing and damping, and MATLAB for such things. So you've dealt some with spring and mass. You have a homework problem about a hanging mass. That homework is due today, or is that the one that's due next week?
Next week.
Next week, but somebody was already working on it. Okay, so the problem you're going to have is, assuming you have a spring and a mass. This spring is maybe a little bit hard to see, but there's a spring here. And you hold it at some point. What is the motion of this thing? Well, it's very much the same stuff you've been seeing since high school physics. This is that same famous problem. It's oscillating. The only thing you'd like to get good at now is trying to figure out where is it oscillating. So when you write the equations of motion for this thing, you'd like to say the acceleration is proportional to the distance from here. Where does it come from? Well, it comes from a mixture of the spring and gravity. Where is this place down here? The equilibrium position relative to this point up here is the rest length of the spring plus the stretch of the spring due to gravity. And you'd like to be able to work out the equations for that and get it right. So I'll start to set that up for you, and then you'll do it on homework. Now, if you take a system like this, there's some things to observe about the motion. One is that if you hold this just completely still, eventually the motion will damp out. So we'd like to be able to put some friction in this. That's a mixture of these velocity-dependent forces and spring forces, which we have not put together yet. So after time, this will damp out. There's not a whole lot of friction here. The next thing is, if I move my hand up and down, if I move it up and down fast, well, what happens? Well, one thing is this is just bobbing up and down anyway, so I want to get rid of that and just see what's left over due to my hand moving up and down fast. And it moves up and down a little bit. If I move my hand up and down very slowly, it goes down with my hand and up with my hand. But if I figure out what's called the natural frequency, this is this cosine, the square root of k over mt, this oscillates. And if I move my hand up and down at that frequency, I barely have to move my hand up and down. And after a while, I get big motions there. Okay, so that phenomenon is called resonance. It's a little bit more complicated than most people make it out. And the reason it's more complicated than most people make it out is the following. That what you learn how to solve in, say, Math 293 is this system, the oscillator system, with a forcing function as a function of time. And you can look at this amplitude and what this amplitude of motion is depending on the frequency of this forcing. If I take a system like this myself and I try to get resonance, I don't pick a frequency with my hand. Instead, I pay attention to what this is doing and I synchronize my hand motion with the motion of the spring. Which means there's another whole dynamic process going on which is in my brain doing this synchronization. People still call this resonance because I'm moving my hand up and down at the same frequency as this. But it's really a slightly different phenomenon because it involves the dynamics of my brain picking this right motion to stay synchronized with this. And if you don't quite stay synchronized, we'll see what happens. Hopefully I'll get to that in a simulation in class today. The same demonstration I just did is here in a machine. This is the machine used in the lab that we're not doing this semester, but which was done for every semester for the past 30 years. And this is now a spring and an oscillating support. There's this sinusoidal oscillation here, which comes from a mechanism called a Scotch yoke from this piece going in circles. This measures how much this top part goes up and down. This measures how much this bottom part goes up and down. These devices are called LVDTs, linear variable displacement transducers, and this could be connected to an oscilloscope. This displacement is fixed in amplitude but variable in frequency, and what we can see is what the response is. At high frequency, this goes up and down a little bit. At very low frequency, it goes up and down. The bottom just goes up and down following the top. And at some in-between frequencies, I can get pretty big amplitude motion if I get it right at so-called resonance. And if I got it just at resonance, the amplitude would be infinite if there was no damping, but there is damping. You can calculate how big the motion is using stuff you learn in Math 293. You should be able to do it, but I'm not going to spend a lot of lecture time on these analytic solutions. Okay, before I get to the blackboard, where I want to just set up this problem, set up the differential equations, and then simulate them on the computer, I'll just tell you a story. Okay? Resonance is a big thing in engineering, in the real world, because everything is a little bit elastic and everything has mass. So wherever you go, you can do things like pound a table, and there's a little pitch to that, ba, ba, and that's because this has some elasticity and it has some mass, and so it has some natural frequency. If it's a simple system, you'll get a simple sine wave response, and that's like musical instruments, strings vibrating and wine glasses and the air in a flute and so on. But this is all over the place, and probably, you know, at the beginning of the semester I said dynamics is not as important as statics because millions of engineers are doing calculations of bending moment and so on, and not so many are doing these simple dynamics calculations. But one exception to that is the science of vibrations. Lots of people are worried about machines vibrating. They cause buildings to vibrate, earthquakes causing buildings to vibrate, machines making noise, car engines making noise. So the science of vibrations is done by lots of people. Okay, so here's now the story I wanted to tell. It's in the book, so apologies to those of you who already read it in the book. But this is a true story. About 10 years ago, I was in San Francisco, and I was walking across the Golden Gate Bridge on Christmas Day. And the Golden Gate Bridge has these big cables which hold it up, these parabolic ones, these vertical ones. Those vertical ones are about this big around, and they're like 50 or 100 feet high. And I thought, oh, they can vibrate. What if we get resonance? Can we get some noticeable motion? So I started on the short strings, which are like, I don't know, 50 feet high, and you push it, and you can sort of feel it move a little bit, and you get in sync, and you push it, and then this whole string vibrates. There's tons and tons of material. You get to the longer strings, and the period of vibration is lower. It's like something like this. And if you go up to it and you try to make it oscillate, you kind of can't do it, because it would be like my trying to make this thing resonate, starting here, but I'm only allowed to move my hand here 1 microinch, and the motion I get down there is too small to see. I only get the resonance if I'm synchronized for some amount of time to get enough motion. But if you work your way down the bridge from the short strings to the long strings, and just remember the frequency at the last one, and then just apply that to the next one, just remember the frequency. Then after you push 5 or 10 times, there starts to be detectable motion, and you can push it more and more. And this giant bridge, the Golden Gate Bridge, with these big things, you get this big wire to actually move big distances back and forth like that. I know it's 50 tons of material waving back and forth, and the cars are all going by, and I was doing this, and I thought it was great fun. And everybody was scared, because it's scary seeing, you know, this big bridge and this big piece of metal going back and forth. And I was doing that, and this police car pulls up and stops and pulls out the megaphone, and this is exactly what they said. He said, "If you break it, you have to pay for it." Okay. Yes, true story. Anyway, so you can play with this resonance stuff, and it's in the book, and apologies, it's both places. Okay, you can play with this stuff all over the place if you want to. Okay, so let's set up this problem of a hanging mass. And we're going to have an oscillating support. And we're going to have with some air friction. And we'll make a bad model of the air friction just so we can get it into the equations the simplest way that we can. Okay, so the model is going to be like this. We're going to pay attention to distance we'll call down positive. And then we're going to have this support, and the support can be using the same Scotch yoke design, which is used in that little machine there, which is there's a pin here, which is connected to a lever, and this thing is connected to a base like this, and this thing is spinning in circles, so this point goes up and down. And let me have it spin in circles the other way. So this point is going up and down. The height of this point is the sine of this angle times this length. So this distance that this goes down relative to this point I'm going to call 0, this distance here, I can call it x0, is going to be d sine omega t. So that's, this little pivot is spinning in circles, is sliding in the slot. This whole thing goes up and down, and then connected to this is going to be our spring, which is down here connected to the mass, and we're going to pay attention to the position of the mass this way. This spring has some spring constant and some rest length. Okay, is that picture clear? Or any questions about that picture? So here's a motor spins with what's called angular frequency, which means the number of radians per second, omega. Okay. So now we want to figure out the equations of motion of this thing. We draw a free body diagram. The free body diagram starts by isolating the system we're going to look at. The first thing we're going to cut away is the world, and we have to fool the thing into thinking the world is there, so there's a force mg here. Then we're going to cut away the spring, and we're going to fool it into thinking the spring is there by cutting the spring and putting this fooling force like this. And then we'll also have some air friction force, so we'll call it a drag force, which looks like that. Now what is the spring force? The spring force is the spring constant times the length of the spring minus the rest length of the spring. That's the spring tension. And the length of the spring is x. So this is k times x. And now what is the length of the spring? It's x minus x0. That's the distance from x back up to the support, and then minus the rest length of the spring. So this whole thing is what we would call delta L, and that's equal to the increase in length of the spring. Increased stretch of the spring. So it's easy to make sign errors if you don't set this up carefully. What I recommend is from this point in your life forward, or maybe that's from a week forward, all things are in tension. Tension is positive, stretch is positive. If something is in compression, you call that a negative tension. It's much easier to do problems that way than it is to try to psych out when it's in compression, when it's in tension. Okay, are there any problems with this formula right here? Okay, then we also have the force of drag, and let's say the force of drag is some constant, some drag constant, times the velocity, and we're going to say that's x dot. Now we're going to use linear momentum balance to get the equations of motion. Linear momentum balance says that the sum of the forces is equal to the mass times the acceleration. And we say, what are the forces on this? Well, we have mg in the plus x direction. Why do I say plus x direction? It's mg times a unit vector in the direction of the arrow. Then we have minus t. Why do I put a minus sign here? It's because I drew that arrow up. Why did I draw that arrow up? Is because I had separately a free body diagram of the spring itself, which looks like this. The spring has tension in it, and by action and reaction, that's pulling away from the mass. And then I have also minus the force of drag equals mx double dot. Now I can substitute in what the formulas I have for these tensions and so on. So I have mg minus that tension. The tension was k times x minus x0 minus L0. x0, remember, was d sine omega t. That's going to be our forcing. And then we also have minus some constant times x dot equals mx double dot. Now there are two standard ways to organize this equation. So this is it. We can rewrite this equation in two standard ways. One of them is the Math 293 way. It's the way of setting things up for the analytic, the closed form solution of linear differential equations. That's if you want formulas for the solution of differential equations, like you learned in 293. And the other way is to rewrite it to set up for numerical solution. So the first way, I'll put like A, something like that, is standard linear ODE way. And what that way is you put all the x stuff on one side of the equation and all the other stuff on the other side of the equation. So you take all the x stuff on one side of the equation. In this case, we have an mx double dot on one side. We have a plus cx dot on this side. And then we have a plus kx on this side. And then we put all the other stuff on the right-hand side. And what do we have on the right-hand side is an mg. So now I've got this term, and I've got this term and this term, and now I'm still missing this kx0. So I have plus kx0, and I also have plus kl0. And this one, remember, was d sine omega t. So one approach to try to figure out how this thing moves is to try to solve this differential equation. So we look for solutions of this differential equation. And what's the nature of the solutions? Well, we can find a homogeneous part and a particular part. The particular part, we can find two particular parts, one associated with the constant forcing, one associated with the sinusoidal forcing. So we end up with a sum of three terms in the solution. Depending on what you're doing, you're interested in different features of that solution. For example, if you just want to know what the oscillation is like, if I hold everything still, I put a 0 over here, and that tells me about the oscillation. If I want to know where it's hanging when everything is still, then I set these two terms equal to 0, everything is still, and I find out what value of x, set this equal to 0 because this is still, what value of x balances these two things. That's finding the static solution. So that's a particular solution which is of interest, setting this equal to 0. And if you're interested in vibrations, then it's the last thing which you're interested in, which is the particular solution associated with this thing. Okay, so for vibrations, what we're interested in is the particular solution, which is the steady state solution as opposed to the transient solution of mx double dot plus cx dot plus kx is equal to d sine omega t. And what is that solution? That solution will be of the form a cosine omega t plus b sine omega t. And the key result is that a squared plus b squared is big if omega is close to the square root of k over m. And that's what we call resonance. So that's the main idea in this vibration thing, is that there's a constant solution where it hangs. There's a transient solution, how it oscillates and decays if there's no forcing. And then there's a steady state solution, which is the sinusoidal oscillations we see over here after this settles down. There's a transient solution. There's the where it hangs solution, that's putting a constant on the right side. And then there's a steady state solution, which is that this thing moves sinusoidally. After the transient, this settles down sinusoidally. And we look at this motion, and what we see is it's not necessarily exactly in phase with this one. So if this is a sine wave, this has a sine and a cosine, and it's got some amplitude. And if I do if I force it at something close to the natural frequency, then this A sine plus B cosine is big. That's the big result. Okay, any questions about that? Somebody please ask a question. Yes? What does what? I can't hear you, so you have to say louder your question.
It looks like 4 vibes
For vibes it says 4 vibrations. We are interested in the particular solution of. Does that answer your question? Okay. Yes?
How do we know that drag force?
Why did I put this term here? When I could have put, for example, C x dot times the absolute value of x dot, which would be quadratic drag. Or I could have put in it was a constant times the sine of x dot. So these are 3 different candidate drag laws. Which one is most accurate for this particular system? Any guesses on that? Who asked the question? So this system is dominated by sliding friction on this rod. And the sliding friction is more or less independent of velocity. That's the way sliding friction tends to be for dry things. And the most accurate model for this system is probably the last one of those 3. If this wasn't sliding and it was moving in air, the more accurate model is probably the quadratic drag, because this is a big, fast-moving thing. And I put the linear drag up there. Why is that? Because that's the one that's mathematically easy. That's the one that's famous. Back in the 19th century and through most of this century, people weren't so good at computers, and they put in this linear damping because they could understand it. And with that linear damping, we can understand concepts of resonance. We can do calculations. So people use that model of the friction, even though it's not necessarily a very accurate model. Okay? So the sort of subject of vibrations is based on this linear damping model, even though for systems with friction, the last one, that is that it goes with the 0th power of velocity, just the sine of the velocity, or the quadratic one is the more accurate one. Okay? So why did I use it? It's because that's the classic thing to do. Now what's one reason that maybe it doesn't matter that much is because lots of systems, ones which vibrate a lot, most of what's going on is with the spring and the mass. The friction is a relatively small term. It's big enough so that you get to some kind of steady state, but not so big that it really matters. So all you want is some term in there which throws away a little energy, and that catches most of how the system works. That was a very long answer to your question. But let's try it again. You asked the question, how do I know it's linear friction? I don't. That's the classic model. Let's just use that for simplicity. Other models will probably be better if we want to understand this in detail. Was the question and answer clear? Okay, yes?
For the particular solution, you drop the mass times gravity and the A times L naught term.
That's
part of the...
No. When you say the particular solution, that's actually not, if you read the book carefully, it's not what the book says. It's a particular solution. It's any old solution. So the way you solve a differential equation like this is you find the general solution to the homogeneous problem. That's the homogeneous solution, or the general homogeneous solution, and any solution to the stuff on the right-hand side. Because this is a linear differential equation, if I can solve it with this on the right-hand side, and I can solve it with this on the right-hand side, and I can solve it with this on the right-hand side, I can add those solutions. So we want any particular solution, and then you want the simplest ones, the ones that don't have this part in it. So there is a particular solution associated with these things, and that's just where the thing is sitting in equilibrium. And what we're interested in is just the particular solution associated with this term. So these terms are there in the general solution of this equation. The part that we're interested in is how big are the oscillations due to the shaking, and that's the particular solution associated with this. Does that answer your question or not?
Yeah.
Yes? Say again? L naught is what we call the rest length of the spring. And it's the distance from here to here when there is no tension in the spring. Okay, so what we want to know is what is the total distance. Are you worried about this? Does that help you? Is that the issue or no? Okay, so what we're interested in is what's the tension in this spring. The tension in this spring is how much the spring is stretched. How much is it stretched? It's the total length of the spring minus the rest length of the spring. The rest length of the spring is L0. How much it's stretched is the distance from here to here. What's the distance from here to here? It's the distance from here to here minus the distance from here to here. And that distance is x minus x0. Okay, details. Does that address your question or not? Okay, so this is the way to write things for ODE solutions analytically, but for numerical solutions, we organize it a different way. We say x dot is equal to v. That's a simple differential equation. And then we have a separate differential equation, which is that v dot is equal to what? It's all this stuff over here divided by m. So I can write it, I could simplify it perhaps, but it's mg minus k times that whole thing minus k times x minus d sine omega t minus L0 minus CV. I think I got everything. And this is then a pair of first order ODEs. Okay. Divided by m. So this is the way we do it on the computer where we don't have analytic solutions. Any questions about that? Okay, now I want to do this on the computer for the rest of the class. Any questions before I get to the computer about the demos, the Golden Gate Bridge, the algebra, setting up the equations? Okay. Laptop. Please control presentation from the connected device. Is that too dark or is that okay?
Too dark.
Too dark. I don't like, the only lights I can control are the one set of lights I don't want. How about that? Good? Okay. So last time, I set up this MATLAB code, and just like last time when we started, when you look at it, you see a blur of letters there, and it looks infinitely confusing and takes some while to settle in and see what you've got. So to start with, you clear, first of all, everything is green, you ignore, because it's there to help you, not to hurt you. So you just look at it to help. You don't look at it as confusion. You look at it as help. So what's left is a bunch of things being set equal to 0 or 1 or 10. So by the time we get to here, all we've done is set a bunch of constants and cleared things. Okay, first bit of confusion is done. Now we're going to have to add some terms here, but I'm going to fix this up bit by bit. Why do we have to add terms? Because we've got this x0 and this omega. We still have this drag constant. We can keep that. Here's one of the parameters we set, which was how many time steps are we going to use to divide up this thing. We did that by picking an h, which was the size of a time step. Let's not start it so small to start with. And we picked a time interval, a start time and a stop time. This tells us how many time steps we have. We turn that into an integer. That's just a MATLAB technicality. Then we set up our future solution, which is going to be an array of time values, an array of x values, an array of v values, and we set them all to 0 to initialize things. So this is just an initialization. Last time I was keeping track of energy, so we could keep track of the error because we knew for a simple problem that the energy was conserved, and we could just see how good our numerical integration was. Then we want to start out putting in our initial conditions, starting time at t0, starting position at x0, starting the velocity at v0, starting the initial kinetic energy at the value of the initial kinetic energy of the system. I think I'm going to drop this for now because it's an extra confusion for my purposes today. So let's just leave out the energy calculation today. So we're not going to check the accuracy of things. Then we do this calculation, which is figuring out again and again predicting the future based on the past. We say we have a new value of x, a new value of v, a new value of t. We have a force law. Our force law is now going to get more complicated. In fact, we want to put the force law all in a different equation, so we're just going to drop these two altogether, and we're going to calculate the force from some other program down here, which is calculating what the force is. So we're going to keep our force calculation separate to keep the logic up here simpler. Then we progress in time by using these velocity and acceleration. We get a new time. We get a new energy. Let's throw that out just to keep things simple now. We fill in the arrays, and then we've got our solution, and then we plot this thing and that. Okay, so now assuming I haven't messed up, what I did last time should still work again. And I get figure 1, figure 2. Figure 2 was about this energy stuff. So let's throw away figure 2. I'll just throw it away. Well, actually, there's something else I'd like to do with it. Let's plot x array and v array. And we can make that blue if we want. And let's just skip the labels now to be fast. Anybody know what we're going to get when I do this plot for this previous problem? Ta-da. Is that a circle? So it's a circle if you pick the axis right and the parameters right and so on. If you want to get things just right, you go axis square. And then you also go axis equal. And this makes the plot square, and it uses the same scale on both of them. And then we run this again, and we get the circle. Why is it a circle? It's because I picked k and m to both be 1. If k and m were not both 1, it wouldn't be a circle. The meaning of the word circle is not even clear because the units are different on the x and y axis. One is position and one's velocity. But if you make it non-dimensional, or you use or you just use meters, kilograms, and seconds, and use a spring constant of 1, a mass of 1, then you get a circle. But not quite. See, it opens up over here. If we want to get a sense of that opening, let's pick our time step to be, say, a cute one is 2 times pi divided by 8. Anybody know what we're going to get now? See, it's spiraling out. And that was that error I showed at the last class. And I think 1, 2, 3, 4, 5, 6, 7, 8. This didn't do quite the thing I wanted it to do, but never mind. If you pick it just right, you can get it to come right back to the x-axis. I think, how about h is equal to 1? See, you get this nice octahedral thing. It's cute. Okay? Any questions about that? Okay, now we want to make this forcing function a little bit more complicated. So we're going to put in the right-hand side, it's going to be done in x, v, t. Let's get our parameters down in here. We had a k as a parameter. We had a c as a parameter. We have our the mass we don't need as a parameter. We had our omega as a parameter, the forcing function omega. And then we need to get we need to make sure that all this stuff matches when we call this function. So back up here where we called the function, it was this stuff in here. So we've got to call it with all that stuff. And that means I have to make sure I've defined my omega, which was my, my forcing frequency. So I'll pick an omega is equal to some thing. Let's just pick it as 0 to start with. And I also had a forcing amplitude. And let's just set that equal to 0, 2 to start with. And this was the forcing frequency and forcing amplitude. I'll post this so you don't have to take notes. Okay. So that means we also have to pass in the D here, which was the forcing amplitude. That means down here we've got to have our D here. And now I have to copy in that whole complicated force. I see something else I left out too, which was the L0. So what was the force on this thing? It was K times a bunch of stuff. What was the stuff? It was X, and it was a minus, the force was a minus K times the stretch of the spring, which was X minus the D times sine omega t, sine of omega times t, and also minus L0, and also minus C times V. It's not wrong, it's just different. Let's see, that means I have to put up here also another parameter, which is L0. I need to pass that in too, which is a pretty boring parameter in this problem. But just to make it complete, let's say we're doing an engineering calculation and we care where things are, not just how much they move. We would want to get the L0 right too. So let me put that in as 0 to start with. So that's the rest length of the spring. Because of this hiring the handicapped policy I told you about. So we have plus m times g. Did I remember it over there? I remember it over there. Okay. So now we have this new system. The way I've set it up is very much the same as the old system because I put in no forcing amplitude. The rest length I put was 0. The forcing frequency I put was 0. The damping, okay, I have a little damping in here. Let's put that damping equal to 0. And now I should get the same thing again. In fact, I can't tell if I get the same thing again, so I better put in a different time step h. Where was my h? Up, 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 up. So I go 0.1, and now I get this thing with some error. Okay. Too many input arguments. Test right has too many inputs. Line 30. Line 30, I have da 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 da. And when I went down here, I didn't stick in my L0, right? Or my M. I don't need my, oh, I need my M too. And I need G too. What a pain in the neck. Okay, so I need G and M. I need all those things in here. So just to make sure I've got them in the right order. Order here is absolutely key because MATLAB just sticks things in the right place and doesn't pay attention to the names. And I'm going to teach you a way to avoid name confusion, but that's not going to be today's lecture, by passing in a structure rather than passing in all the variables separately. Okay, so now it should work, I hope. Ta-da. And let's not look at the phase plane particularly. There's this thing, the oscillation is not, we've got pretty much numerical error. We want to reduce the numerical error. Let's make our step size smaller. Then we get a decent numerical error. The circle almost closes up. Okay, let me just skip figure 2 for a while, look at figure 1. Is green clear enough to see, or do you want a darker color there? Darker color, so figure 1, we had green. Let's try red. Red better? Okay. Figure 2, I just don't like figure 2. But I don't want to totally get rid of it either. Okay, so now we can play around with this thing. So let's do something. Let's run this thing for a longer time. So let's run it for 20 pi. And now we can see the effect of these different parameters. Okay, 20 pi is not being so accurate. So we're seeing this growth in amplitude, which is not a real growth in amplitude. So let's get this accurate enough so that we can see the effect of things. So now there's a little bit of growth of amplitude. It looks like a kind of negative damping, and that's a numerical error. So let's just pretend this is constant because I don't want to wait all day for the solutions. Now let's add some features to this motion. Like let's put in a little damping. If I put in a little damping of 0.1, what's going to be the motion? Well, this is, we can get, the way I've set the constants here, this is just getting the homogeneous solution. The homogeneous solution from differential equations is an exponential multiplied by a sine wave, and there's your exponential multiplied by a sine wave. Notice there's no exponentials or sine waves in this code at all. This is just what the numbers make happen. The numbers are kind of analogous to the physics. We're just lucky that for some problems like this one, you can get formulas for this stuff. But even without the formulas, it does what it does. It's exponential decay. Yes? Yeah, the homogeneous in particular has to do with the right-hand side. The damping is still on the left-hand side because it was a constant times x dot. Okay, so that was with the mx dot plus mx double dot plus cx dot plus kx equals 0. So this is the damped homogeneous solution. I can put in bigger damping here, like a 1, and then it will be very damped. There's a keyboard, see, quite damped. I can put in even a bigger damping, like 5, and then it doesn't even decay as fast. And I can put in a bigger damping, like 50, and then it barely decays at all. So what happens if you have huge damping? It just locks the system up, and it takes a long time to decay. If you have teeny damping, it oscillates for a long time. And there's some in-between value of damping where it decays fast and doesn't oscillate. And that's roughly called critical damping, which is right when the square root in this quadratic equation that you should be familiar with has the thing inside the square root is 0. Okay, so that's the damping side of things. Now let's look at the forcing side of things. Let's go back and make the damping pretty small, 0.1. And now let's force this at some omega, which is not 0. But let's put omega to be, see, omega equals 1 was the natural frequency of this thing. So let's put in omega of 0.1. So it just oscillates a little bit. But let's make the amplitude of oscillation pretty big so we can see it. Let's put it in like 2. And then what do we see for this motion? Is that there's the sinusoidal motion, and superposed on that is the motion of the forcing going back and forth. Let me do this for a longer time, and you'll see that forcing function more clearly. So what's happening is you have this homogeneous solution damping out, and then you have this particular solution from moving the support up and down, and it's superposed on top of that. So you see this clear superposition of the homogeneous plus the particular solution. Now if instead I put in a very fast forcing, like omega equals 5, pretty fast, then it's all tangled together, and it's hard to see what's what, but there you see left over is this 5 times the frequency oscillating back and forth with very small amplitude. Remember, I shake it very fast, and the support doesn't, and the mass doesn't move very much. Then the in-between case, if you force it at about the frequency that it wants to oscillate anyway, then that's the resonant case. And what you see is that the motion grows to be very big. And in fact, if we want to see that growing even better, we can start this one with 0 initial condition. So it starts out with no oscillations, and we run this thing and we see it grows like this. Okay, we can make the forcing even smaller in amplitude by making this d equals 0.2, and we can watch this grow. Let's see, 0.2, getting the initial condition 0, what's the meaning of 0 is the hard part here. Let me go back up to that 2, and let me make the damping smaller. Now I run this thing, and the amplitude increases and increases. So this is like me with the Golden Gate Bridge. If I run this for a long enough time, let's put in 200 pi now, eventually it will get to steady state. See, it's approaching steady state. The smaller I make the damping, the longer it takes to get to steady state. Now if I make the damping exactly 0, it never gets to steady state. And it just increases linearly in time. It looks like a little curve there, but that's the numerical integration error. It just grows linearly in time, and that's back in Math 293 language, the solution t times sine of t. That's this weird double root case. Okay, now what happens if I force it a little bit different from the resonant frequency, but there's no damping? This is an interesting case. Anybody know what this does? So I'm forcing it almost at the resonant frequency, and there's no damping. I like this one. What happens is, let me make it a little closer so you can see it better. 1.02. What happens is if you just look for a small amount of time, it looks like resonance, and then it gets all eaten up again, and then comes back and gets all eaten up again. And this is a very mathematical thing, because it only happens if you have no damping. You just put in a little bit of damping, and then being close to resonance means it increases up to some steady state. So eventually that just levels out at some steady state. Okay, any questions? Okay, class today was boring, raise your hand. Interesting. Too interesting. I got to meter it. I don't want to make it too interesting, you know, so it's got to, okay, so get out of here.